In today's video, we will be learning about modified Booth's algorithm and how to multiply two different values using modified Booth's algorithm. The advantages of modified Booth's algorithm are we call them as fast multipliers, and here we use reduced number of bits for multipliers. Since we use reduced number of bits for multipliers, automatically the summons will be reduced. After performing the modified Booth's algorithm by multiplying two different values, we'll try to check and verify whether all these three advantages are met. So here is a first example. We are taking two different values. One is 10, other one is 12, and we should multiply this 10 and 12 using modified Booth's algorithm. That is the first example that we are considering. So what is the equivalent of binary equivalent of 10? It is 0, 0, 1, 0, 1, 0. What is the binary equivalent of 12? It is 0, 0, 1, 1, 0, 0. So we are considering these two values 10 and 12, and we are going to multiply these two numbers using modified Booth's algorithm. In order to do that, the first step is to select the multiplier alone. We are not worrying about the multiplicand, just we are selecting the multiplier. What is a binary equivalent of multiplier? We have already discussed in the last slide. It is 0, 0, 1, 1, 0, 0. Now, in the second step, we have to recode this binary value into a different form called Booth recoded version. In order to do that, we have to remember this table. Whenever there is a transition from 0 to 0, your recoded value will be 0. When there is a transition from 1 to 0, it is plus 1. When there is a transition from 0 to 1, it will be minus 1. When there is a transition from 1 to 1, it will be equivalent to 0. We have to remember this. With that as an idea, the second assumption is we are being given with the binary equivalent of the multiplier. Whatever the multiplier may be, we have to append a 0 at the back. To be very clear, after the least significant bit, we have to append a 0. And we have to start recoding from this bit only. So, right now, whenever there is a transition from 0 to 0, what is the recoded value? It is 0. Therefore, we can write it as 0. When there is a transition from 0 to 0, the recoded value will be 0. When there is a transition from 0 to 1, what is the recoded value? Transition from 0 to 1 means it is minus 1. Therefore, it will be minus 1. When there is a transition from 1 to 1, it is 0. And from 1 to 0, it is plus 1. From 0 to 0, it is 0. So, right now, we have calculated the Booth recoded value of the multiplier. Next, we have to calculate the bit pair recoded value of the multiplier. So, in the previous slide, we have obtained 0 plus 1, 0 minus 1, 0, 0. We have to pair in this way 0 plus 1, 0 minus 1, 0 and 0. Just two bits together. So, we are rewriting it again, which is 0 plus 1, 0 minus 1, 0 and 0. We are rewriting this value. So now we have to find the bit pair recoded value of the multiplier. How to do that? Let us do it one by one for each and every pair. We'll start with the first pair 0 and 0. What is the binary weightage here? It is 2 power 0, 2 power 1. What is the equivalent of 2 power 1? It is 2. So 2 into what is the value present? It is 0. Plus what is 2 power 0? It is 1. 1 into what is value here? It is 0. So 2 into 0 is 0. 1 into 0 is 0. 0 plus 0 will be equal to 0. Therefore, the equivalent of bit pair recoded equivalent of this pair is 0. And now, let us take the second pair. It is 0 and minus 1. Again, we have to put 2 power 0, it is 2 power 1. What is 2 power 1? It is 2. So 2 into what is the value present here? 0. Plus, what is 2 power 0? It is 1. What is the value present here? Minus 1. So 1 into minus 1. 2 into 0 is 0. Plus 1 into minus 1 is minus 1, which is equal to 0 plus minus 1 will be minus 1. Therefore, the equivalent of this pair 0 and minus 1 is minus 1. There is another value here, 0 plus 1. 0 plus 1. This is a third pair. So what is the equivalent? It is 2 power 0 and 2 power 1. So 2 power 1 means 2 into what is the value here? 0 plus 2 power 0 means 1. 1 into what is the value here? Plus 1. Therefore I am writing as just 1. Maybe we can write it as plus 1 itself. So it is 0 plus 1 into 1 will be 1. So 0 plus 1 will be equal to plus 1. Okay. So the equivalent, that is bit pair recoded value of this pair 0 and plus 1 is plus 1. So therefore plus 1 minus 1 0 is now the multiplier value, which is nothing but the bit pair recoded equivalent of the original multiplier. Now we have to check whether this plus 1 minus 1 0 is equal to the original value of the multiplier. What is a multiplier binary value that we have assumed? We assumed it to be 0 0 1 1 0 0, and we said that it is nothing but 12. Right now we have plus 1 minus 1 0. Whether this is equal to 12, we have to check. How will we calculate the binary equivalent of 12? We generally write as 2 power 0, 2 power 1, 2 power 2 and add everything and see whether it is 12 or not. But here we have clubbed two values together and finally recoded this multiplier. Right now this weightage will be equal to 4 and not 2. Therefore we have to write it as 4 power 0, 4 power 1, 4 power 2. Okay. So what is 4 power 2? It is 16. 16 into 1. Plus, what is 4 power 1? It is 4 into, what is the value here? It is minus 1. Plus, 4 power 0 means 1. 1 into 0. Therefore, this can be 16 into 1, 16. 4 into minus 1, which is equal to minus 4. 1 into 0 will be 0. So what is 16 minus 4? It is 12. Therefore, the recoded version plus 1 minus 1 0 is also equal to 12. Now both are correct. But check out how many number of bits you have. 1, 2, 3, 4, 5, 6. Instead of 6 bits, how many number of bits you have here? 1, 2 and 3. So we have reduced the number of multiplier bits. Okay. So right now we are going to perform multiplication operation with the multiplicand and this reduced multiplier. So now let's start our multiplication. We are ought to multiply 10 and 12 and result in 120. We have to do that now. Okay. So for that, what is the equivalent value of 10 that we have already written? It is 0, 0, 1, 0, 1, 0. We have to multiply this value of 10 with recoded, that is bit pair recoded multiplier value. What was it? It was plus 1, minus 1 and 0. So now we have to start multiplying. First let us consider 0. 0 into any number becomes 0. Therefore 1, 2, 3, 4, 5, 6. Generally, if we multiply 6 bits along with another 6 bit of data, generally we have too many number of partial products, and here we will have 6 set of summings. Right now we have only 3 bits, so we are going to have only 3 different summings. That is why we say that we have reduced the summons also. In order to balance the partial product, we are adding another 6 bits here. So 3, 4, 5 and 6. It is not this just we have to append 0. Whatever bit is here, we have to replicate the same bit here. Okay. So this is the first step. Now, since it is a radix 4 value, it is not a binary base, it is a radix base, but this number is binary base. So it is not enough to just shift one bit, we have to shift by 2 bits, because what is the equivalent here? It is 4 power 0 means 1, 4 power 1 means it is 4. 4 is equivalent to 2 power 2. So we have to start at 2 power 0, 2 power 1, 2 power 2. These two are equal. So when we start counting from this location, it is 2 power 0, 2 power 1, 2 power 2. Therefore, when we want to multiply this particular value with our multiplicand, we have to start in this location of 2 power 2 only. Okay, so we'll start doing that. Right now, what we have to do, we have to multiply this particular multiplicand with minus 1. Minus 1 in the sense it is a negative value. So, in order to multiply, we have to find the 2's complement of multiplicand first. So, let us do that. So, we have 0, 0, 1, 0, 1, 0. Let us assume it to be m, which is the multiplicand. So, we have to find 1's complement of m. What is it? Just inversion. 1, 1, 0, 1, 0, 1. Add 1 along with it. So, what will be? So, 1 plus 1, 0. Carry 1. Again 1. 1. Therefore, 1, 0, 1, 1. This is the 2's complement form of m. We can rewrite the same here. What is it? It is 0, 1, 1, 0, 1, 1. What is the bit here? It is 1. Therefore, we can just replicate these bits. It is called sign extension, because this is not going to cause any change. Therefore, we are just extending this sign bit everywhere. Now, we have to multiply with plus 1. In order to do that, we have to jump by 4 steps. Okay, because this is 4 power 0, 4 power 1, 4 power 2. 4 power 2 is equal to 16. When you look at this value, 2 power 0, 2 power 1, 2 power 2, 2 power 3 and 2 power 4. What is 2 power 4? Again, it is equal to 16. Therefore, this location is equivalent to this plus 1. Okay. So, if it is just plus 1, we have to copy and write the same detail here. So, it is 0, 1, 0, 1, 0, 0. Extend the sign bit here, 0 and 0. Now, we have to perform normal addition. It is just 0, 0, 0, 1, 1, 1, 1. Again 1 plus 1 will be 0, we will have a carry. 1 plus 1 will be 0, we will have a carry. 1 plus 1 will be 0, we will have a carry. 1 plus 1 is again 0, we will have a carry. 1 plus 1 will be 0, we will have a carry. And let us stop it here. Now we have to calculate, because it is enough with your partial product bits. It is 0, 0, 0, 1, 1, 1, 1 and followed by lot of zeros. Now, if we try to calculate the equivalent value of this one, it will be 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5 and 2 power 6. So, what is 2 power 6? 64 plus 32 plus 16 plus 8, which is equal to 120. So, we were about to multiply 10 into 12 and we got the answer 120, and using modified Booth recoding we tried to multiply and obtain the same 120. But if you generally multiply 6 bits into 6 bits, we generally have 6 different steps here. Instead, we used only 3 bits as multiplicand and reduced the summand also. Therefore, thanks for watching.